My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the magnetic field of the electric current. Movement of charges create magnetic field. In this edition, we'll be able to learn about the magnetic field due to current carrying straight wire, current carrying circular coil, and solenoid. So let's get started. The motor effect or force of the magnetic field on a current carrying straight wire. Actually, it is an experiment in which the energy is converted from electric energy into mechanical energy. So we've got conversion of energy from electric into mechanical energy. As a matter of fact, when a current is passed through a wire and the wire is placed perpendicular to a magnetic field, the wire moves because the wire will be acted upon by a force. A force will act on the wire. Okay, to determine the direction of the force, to determine direction of motion, we use Fleming's left-hand rule. So talking about Fleming's left-hand rule, okay, it is used for determining the direction of motion when a current causes motion. What does it mean when a current causes motion? It means we've got a wire placed in a magnetic field and a current is passed through the wire and wire moves, so we call it current causes motion. We start with current, allowing the current to flow, then the wire moves. Okay, we'll use Fleming's left-hand rule to determine direction of motion or direction of the force of the magnetic field that act on the wire. What about Fleming's left-hand rule? It states that place the forefinger, second finger, and the thumb of the left hand mutually at right angles, mutually perpendicular. Then, if the forefinger points in the direction of the field, second finger in the direction of the current, conventional current of course, the thumb will point in the direction of the force, direction of motion. Okay, so once again, forefinger points, yes, in the direction of field. Okay, second finger points in the direction of the conventional current. The thumb automatically will give the direction of motion or direction of force. And don't never forget, we'll apply Fleming's, yes, left when current causes motion. So when a current carrying a straight wire is placed at right angles to a magnetic field, the wire moves. There'll be a magnetic force acting on the wire. The wire moves due to the interaction between the two fields. Okay, the magnetic field of the current carrying wire and the uniform field of the magnet interact. So in front of you shown the interaction of the two fields. Okay, we've got a magnet, okay, the field of the magnet is uniform. What does it mean the field is uniform? It means it is composed of, yes, straight flux lines which are equally spaced. And we've got a wire carrying current. Current is moving out of the screen, okay? The two fields will interact. On one side of the wire, they'll have the same direction. On the opposite side, on the other side, the fields will have opposite directions. Okay, so this is the result of the interaction. The fields on one side increases where the two fields have the same direction. On the other side, the field density decreases. Okay, and don't never forget that flux lines tend to repel each other sideways. Okay, so a force is generated, is produced on the wire. The wire experiences a magnetic force. So as shown from the previous figure, when the two fields combine, the magnetic flux lines get closer on one side of the wire, okay, where the lines of the two fields are in the same direction. We call this region a region of high magnetic density or intensity. Okay. The flux lines are set apart on the opposite side where the lines of the two fields are in opposite directions. And of course, this is a region of low magnetic intensity. The wire moves away from the region of higher intensity to that of the lower intensity. And now talking about the factors that affect the force, the magnetic force acting on a current carrying a straight wire. Talking about factors affecting the force of a magnetic field on a current carrying a straight wire. First of all, the force is directly proportional to the current intensity, the current passing through the wire. Okay, so the force is directly proportional to the intensity when the rest of factors are kept unchanged. Also, it is directly proportional to the length of the wire. The longer the wire, the greater the force. The longer of the part of the wire in the field, the greater the magnetic force. Okay, second, other factor is the strength of the field, magnetic flux density. Okay, and of course the force is directly proportional to beta. And finally, sine of the angle between the angle that the wire makes with the field, sine theta. All these factors will be combined. So F is proportional to BIL sine theta. Once again, B is magnetic flux density of the field affecting the current carrying straight wire. I is the current intensity through the wire. L is the length of the wire in the field. Theta is the angle between the wire and the magnetic field. Okay? Proportionality sign is replaced by equality. We expect to find a constant. It is denoted by K. But the constant is equal to 1 when the unit of magnetic flux density is Tesla. So the expression will be just F is equal to BIL sine theta. Okay? It is BIL sine theta. This is the expression that gives the magnitude of the magnetic force acting on a current carrying a straight wire. Magnetic flux density beta. The magnetic flux density of a uniform magnetic field at a point is numerically equal to the force. Okay, it means we can now give another definition of magnetic flux density. It is equal to the force that acts on 1 meter in length, okay, and carrying a current of 1 ampere that acts on a wire, 1 meter in length and carrying a current of 1 ampere, and placed at right angles to the field. Okay, so how we managed to give this definition? It's all easy. Since beta is equal to F over IL sine theta, so beta will be equal to the force when I equals 1 ampere, length of the wire is 1 meter, and theta is 90. Theta is the angle between the wire and the field. Okay, So magnetic flux density is the force that acts on a wire 1 meter in length carrying a current 1 ampere and placed perpendicular to the field. And now we want to define Tesla. What about Tesla, unit of magnetic flux density? Tesla equals Newton over ampere meter. So what about Tesla? Tesla is the magnetic flux density of the uniform field. It is magnetic flux density of the uniform field, which exerts a force of 1 Newton on a wire 1 meter in length, carrying a current of 1 ampere and placed at right angles to the field. So we managed to give definition to magnetic flux density and to define its unit, to define, yes, Tesla. And now we've got a question we want you to answer. What's meant by the magnetic flux density of uniform field at a point, yes, is equal to 0.02 Tesla. Let me say the question again. What's meant by magnetic flux density of uniform magnetic field at a point 0.02 Tesla? It means a force of 0.02 Newton, yes, would act or will act on a wire 1 meter in length carrying a current of 1 ampere, okay, when placed at right angles, when placed perpendicular to the field at that point. Thank you very much. Okay, your attention please, we've got something here to add. When the wire makes an angle theta with the field, the expression used, the relation will be, yes, F is equal to BIL sine theta. In front of you, okay, we've got a wire, field that makes an angle theta, resolution of the field in 2 components, one which is parallel to the wire, b cosine theta, and it has no effect, and the other component acts perpendicular, b sine theta. So the general expression will be BIL sine theta. Theta is the angle between field lines and the wire. If the wire is placed parallel to the field, it will not experience any magnetic force. The force is then equal to 0. Why? F is equal to BIL sine theta. Theta equals 0, sine 0 equals 0. Okay, this happens when the wire is placed parallel to the field. Okay, field lines are parallel to the wire, force is equal to 0. When the wire is at right angles to the field, of course, it will experience the maximum force, the greatest force, and it will be just BIL, simply because sine 90 is equal to 1. Okay. So this happens when the field makes an angle 90 with the wire. The expression used will be BIL, B magnetic flux density, I current intensity through the wire. And now we've got a question. Explain, a current carrying wire is placed in a magnetic field. So we've got a wire, straight wire, and a current is passed through it and is placed in a magnetic field, but it doesn't experience any force. No force acts on it. What is your explanation? The wire must be placed parallel to the field. Thank you very much. Theta is 0. When theta is equal to 0, the force equals 0, because the force is given from the direction, because the force is given from the expression BIL sine theta, and theta is equal to 0, sine 0 is equal to 0. Force between current carrying conductors and Fleming's left-hand rule. Okay, we've got something very important now. We'll calculate the force between two current carrying straight wires. Okay. Force of your attention, please. Force of the magnetic field of wire B on a length L of wire A. So field of wire B will exert a force on wire A. In other words, wire B will act as a magnet to the other wire, wire A. Your attention. Force of the magnetic field of wire B on a length L of wire A. Okay, in front of you we've got two wires, A and B. Okay, A carries a current I1, B carries current I2. Okay. Force of the magnetic field of wire B is equal to the field of wire B times current, yes, I1 and L. Okay, field of wire B, but when we take the current, we'll take the current passing through wire A. But field of wire B is equal to 2 times 10 power negative 7 I2 over D. Okay, and of course we have I1L. So we can say F produced by wire B, the magnetic force of wire B, is equal to 2 times 10 power negative 7 I1 I2 L over D. This is the first equation. And now we'll do something very interesting. We'll calculate the force of wire A on a length L of wire B. So wire A now will act as a magnet to wire B. Force of the magnetic field of wire A on a length L of wire B. Force of A equals magnetic field of A. Current of B, I2, is the current that flows in wire B, and the length taken or considered of wire B. And of course, magnetic flux density of wire A equals 2 times 10 power negative 7 I1 over D. Okay, these are between two brackets times I2L. So we can say FA is equal to 2 times 10 power negative 7 I1 I2 L over D. This is the second equation. From equation 1 and equation 2, we can conclude that FB, the force produced by wire B, is equal to the force produced by wire A. That's to say, each meter length of the two wires experiences the same force. Let me say it again. Each meter length of the two wires experiences the same force. It means that the force on the same length of each of the two wires is the same. And it is calculated from the expression 2 times 10 to the power of negative 7 I1 I2 L over D. If the medium between the two wires is air, in general, it is F is equal to mu I1 I2 L over 2 pi D, where mu is the permeability of the medium. And now we've got important questions, and we want to answer these questions together. So we've got important answered questions. Mention one use of each of the following. We want you to mention just one use of the following. Maxwell's corkscrew rule. We call it the right-hand corkscrew. Maxwell's corkscrew rule. Yes, thank you very much. It determines the direction of the magnetic field produced by a current carrying a straight wire. Okay. And of course, you know, it's a statement. And it states that imagine a corkscrew being screwed along the wire in the direction of the current. Direction of rotation of the screw gives the direction of the magnetic field. It can be used to determine the direction of the magnetic field at the center of a current carrying circular coil. Mention one use of Amperes right-hand rule. What about Amperes right-hand rule? Actually, it determines the direction of the magnetic field due to a current carrying a straight wire. Let me say it again. Amperes right-hand rule, okay, determines the direction of the magnetic field due to a current carrying a straight wire. One use of Fleming's left-hand rule. Do you remember Fleming's? We use Fleming's, okay, when current causes motion, when we've got a current carrying a straight wire placed in a magnetic field, the wire experiences a force and it moves, and we want to determine the direction of motion, we'll use Fleming's left-hand rule. It determines direction of the magnetic force, direction of motion. Okay, so it determines the direction of the magnetic force exerted by a magnetic field on a current carrying a straight wire placed perpendicular to the field. Give reason for. In front of you, we've got a solenoid and a straight wire, and both of them are carrying currents. But there is something a little bit strange here. The straight wire carrying, the straight current carrying wire shown in the figure experiences no magnetic force, although it is placed inside a current carrying solenoid. Why? Simply because the field of the solenoid is parallel to the wire. Field of the solenoid is parallel to the wire. So the wire does not experience any magnetic force. And it is calculated, the force is determined from the expression F is equal to BIL sine theta. The force is equal to 0 when theta, the angle between flux lines and the wire, is 0. Okay. And now talking about the magnetic torque acting on a rectangular coil, a coil that carries a current and placed in a magnetic field. It will experience a torque. Okay, in front of you we've got a magnetic field, okay, produced by a permanent magnet and a rectangular coil. When a current is passed through the coil starts rotation. Okay. In the horizontal position, it is the position where the plane of the coil is parallel to the field. Magnetic flux lines are parallel to both sides, BC and AD, so they experience no force. But sides AB and DC are perpendicular to the field lines, so they are acted upon by two forces. And what about the two forces? They are equal in magnitude and opposite in direction, and they don't have the same line of action. They'll produce a couple. These two forces are parallel, so they produce a couple, which causes the coil to rotate around its axis. The magnitude of the torque of this couple equals one of the two forces times the normal distance. So if you want to calculate the magnitude of the torque, all you have to do is to obtain, yes, one of the forces, magnitude of one of the forces times the normal distance between the two forces. So torque equals one of the forces is equal to BIL. Normal distance is LBC. LAB times LBC will give the face area of the coil. So torque is equal to BI between two brackets LAB times LBC. It is equal to BIA. As I said, capital A is the face area of the coil. Okay, since area of the coil is given by the product of length of AB times length of BC, length times width. If the coil consists of n turns, the torque is given from the expression BIA n, n is the number of turns, and IAN will be given the symbol MD, magnetic dipole moment. So MD is the magnetic dipole of the coil, and actually it is equal to IAN. Magnetic dipole of the coil is defined as the torque exerted on a coil when placed with its plane parallel to a magnetic field of density 1 Tesla. It is the torque exerted on the coil when the coil is placed with its plane parallel, placed in the horizontal position. It's a plane parallel to the magnetic field, but the field should be of 1 Tesla in intensity. So we can say the torque will be numerically equal to the magnetic dipole when B is equal to 1 Tesla. Okay, unit of magnetic dipole moment is ampere meter square. Thank you very much. This way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.